Hello everyone, welcome to fourth session of this crash course series. Today we are going to see some important and interesting part of organic chemistry, that is none other than isomerism. So isomerism, it is not a separate chapter, it is linked with GOC, General Organic Chemistry, but it is very important to learn about this to solve other problems of organic chemistry, right? I know most of the students are worrying about this part, isomerism. You may miss the class, you may forget about the silly things about isomerism. In this today's session, we are going to crack that. We are going to ace the isomerism chapter. By end of this session, you'll be master in organic isomerism. Okay, so without any further delay, let's get started. First of all, what is isomerism? Iso means same, right? Merism means parts. So isomerism means there will be some similarity but same element in between two compounds. What are they? Let's take it out. So isomerism is broadly classified into two, that is structural and stereo. Today we are going to see both the isomerism. First, structural. It is very simple, okay, but questions can be asked from this part a lot. Structural isomerism, as the name explains, the structure varies. Same molecular formula, but different structural formula, different way of writing it. Okay, so that is structural isomerism. This is further classified into main 6 types. They are chain isomerism, that is having same molecular formula but different arrangement of carbon skeleton. How, ma'am? Yes, we'll come to that. Chain isomerism, you can see the examples over here, that is pentane and isopentane. Pentane, you can write how many carbons? 5 carbons, CH2, CH2 and CH3. Talking about isopentane, iso means 2 CH3 group attached with 1 carbon, isn't it? So isopentane structure is CH3, CH, CH3, CH2, CH3, right? What is the molecular formula of isopentane? 5 carbons are there. How many hydrogens? 3, 6, 7, 8, 9, 10, 11, 12. C5, H12. What about pentane? Once again 5 carbons and how many hydrogens? 9 plus 3, 12 hydrogens. Right? Same molecular formula but different way of attachment in the same chain. Chain isomerism is exhibited by only the carbon chain. No other functional groups are changing. No other substituents are changing. It's just talking about the hydrocarbons. Please be careful with that. Okay. So the second part, that is position isomerism. That is having different positions of functional groups. That is very important. Different position of functional group. Let's say I'm having a functional group of alcohol which is attached in second position. CH3, CHOH, CH2, CH3. What is this? 2 butanol or butane to all. Let's say I'm attaching this functional group in third or first position, let's say. Then that will become 1-butanol, right? I just took that OH and attached with first position. That's it. I'm not literally taking it, but the change in position of the functional group is called positional isomerism or position isomerism. That is second type. The third type is functional isomerism. What is functional group? Amines, OH, COOH, aldehydes, ketone, amides, those functional groups, right? Other substituents as well. If the functional group changes, how the functional group will change? For example, here you can take alcohol and ether. Let me give you the example of, I'm going to erase this. If you are not noted, please note this down. Functional group, what is the general formula of alcohol? That is OH. What is the general formula of ether? Yes, that is ROR, right? So, if I am taking alcohol, CH3, CH2, CH2, OH. This is propanol, right? Alcohol functional group. What is the molecular formula of this? Which is C3H8O, correct? If I'm writing it as an ether functional group, then that will become CH3O, CH2, CH3. What is the name of this? Methoxy ethane. Ether functional group with, what is the molecular formula? C3H8O. Same molecular formula but different functional group. That is called functional isomerism or functional group isomerism. Is it clear? Yes. Now let's move on to the confusing part, so-called confusing part, but it is not. That is metamerism. Remember this, guys. Metamerism is exhibited by the functional group which is having two hands of alkyl groups. What is that, ma'am? What is two hands of alkyl group? Let's say I am considering alcohol. What is the general formula? ROH. Only one R group is attached with that. If I am considering ether, ROR, two functional groups are there. Oxygen is attached with two alkyl groups. That is having two hands holding the alkyl group, right? Metamerism only exhibited by the compounds like this. I can give you another example like ketone. Right? So the metamerism is exhibited by these kind of groups, not for RH or RCOOH or RCHO, RNH2, nothing. Only the functional group which are having two hands. Is it clear? Most of the students do mistake in this part, particularly metamerism. I don't know why, but hope this is clear now. What is metamerism? Once again, that is having same functional, the molecular formula, but different alkyl group attached. Say for example, here I am having ether. As an example, CH3O, CH2, CH2, CH3. Okay. Another isomer of same compound is CH3, CH2, O, CH2, CH3. The molecular formula is same, C4 H8 plus 3 11 3 14 O, C4H14O, H14 H10O. Similarly here also, that is C4H10O. Okay, but the alkyl groups attached with this functional group is getting differed. Here I am having methyl, this side I am having propyl. Here I am having ethyl, another side I am having ethyl. Okay, so please be careful with that. Next functional group, that is tautomerism. What is tautomerism? I am explaining to you with an example. Tautomerism is a reversible thing. Okay, a molecule can go with product side or reactant side like an equilibrium. Okay, say for example, if I am having acetone, CH3, CO, CH3, and if I am having propane 2-ol, how many carbons? 3 carbons must be there. Propane 2-ol. Okay, so how many carbons? 3 carbons. C3H6O. This is also C3H6O, right? Same molecular formula once again, but what happened over here? The shift of hydrogen. This maintains an equilibrium. This is keto and this is enol. The shift of hydrogen happened over there. So it will get cleaved, O becomes negative, so hydrogen get attached with oxygen. So keto-enol tautomerism. Similarly, we have nitro-acinitro tautomerism. But mostly they will be asking about keto-enol tautomerism. You must have seen this in mechanism part. Okay. The last type of structural isomerism is ring chain isomerism. That is very, very simple. If I am writing it in chain, I can write it in ring model also. How? Let's say I am taking propene. Cyclopropane. CH2, CH2, CH2. How many carbons? 3 carbons, 6 oxygen. Right? How many carbons over here? 3 carbons. Sorry, talking about hydrogens. How many hydrogens? 6 hydrogen. So C3H6, same molecular formula. I am writing this is ring and this is chain. Sorry. The next part, that is very simple isomerism type, that is ring chain isomerism. Ring. For example, if I am writing cyclopropane, CH2, 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 C3H6. If I am writing propene, CH2 double bond CH3. The molecular formula is C3H6. Same molecular formula I have written as ring structure, and this is chain. Okay. So this is ring chain isomerism. The questions can be asked from this part for this year. So please be prepared. What isomerism? That is very, very important point to be noted here is where you will get confused. That is metamerism is sorted, functional group isomerism is sorted, positional isomerism, that is very, very, very important. It meant for functional groups only. Metamerism is meant for the functional group which are having two sides to hold their alkyls. Okay, so hope this is clear. If you have any doubt in isomerism, please let us know. We explain it in detail as a separate video. Now let's move on. The next part of isomerism is stereoisomerism. Stereo is not like sound. Stereoisomerism is having different spatial arrangement. Where that is arranged. Structural isomerism is how that is arranged. This is where that is arranged. This is having the further classification of conformational and configurational. Guys, please be aware, conformations and configurations are entirely different. Conformations are the one which are having different spatial arrangement due to rotation about sigma bond. Okay, so let's see this in detail. First, configurational isomerism. Here I am going to take geometrical isomerism first. What is geometrical isomerism? It is having restricted rotation. It is having restricted rotation. What is restricted rotation? Let's say I am having double bond CH2 CH2. Can I rotate this molecule? Is it possible? There is lots of strain. There will be a restriction to rotate this molecule, isn't it? I'm not talking about the rotation in this wise. I'm just talking about the rotation over here. Right? So that restricted rotation is about geometrical isomerism. Let's have some examples of geometrical isomerism so that you will be very clear about that. For example, if I am taking C double bond C, A, and this is B, and this side I am having A and B. Okay. Can I rotate it in this way to form B, A, A, B? Guys, please be aware, I am not talking about rotating the entire molecule. I am just talking about rotating one side. Okay. So, can I get this molecule by rotation? Obviously not. Right? Because the rotation is restricted because of the double bond. So, this is not possible. Which makes this is a different molecule and B is a different molecule. Right? So what would be the name of these? Let's name this depend on the attachments. So here we have two type of configurations. The first one is cis-trans. Cis-trans isomerism. this is if the two similar groups are on the same side of restricted rotation. Then the configuration is cis. Say for example, if I am taking a molecule of this, two groups are on the same side, then that is cis. If that is an opposite side, what does this mean? Then that is trans. Then that will be considered as trans. As simple as that. I'm having a double bond. I'm having a group, similar groups which are attached on the same side, then that is cis. If that is attached on the opposite side, then that becomes trans. Okay? Similar group, note it down. What about the other classification? That is E-is-it. E-is-it isomerism. What is the difference between these two? Once again, this is also deals with the restricted rotation. This is also deals with the double bonds and where the restricted rotation are possible. Here, the important point is seniority of groups. Seniority of groups. What is seniority of groups? Say for example, if I am having Cl, I, H and Br. Let's take one carbon and consider these two substituents, hydrogen and bromine. Among these two, which is having highest atomic number? Of course, bromine. So I'm ranking it 1. Hydrogen will get second rank. Considering another carbon, Cl and I, which is having highest atomic number? Obviously, iodine. So first rank goes to iodine and the second rank goes to chlorine, right? So depend on this seniority of the groups. If that is positioned in the same side, then that is Z. You can remember it like same. This is also having the same sound. Z is also having the same sound. Okay? Z. Just remember it like that. So if that is on the same side, then that is Z. If that is have on the opposite side, the high priority groups are seniority. High priority groups are on the opposite side. Then that is E. This is 1 and this is 1 which is on the opposite side. Then that is E. E for opposite side. Is it clear up to this part? Cis, trans, E, Z. Okay. Is there only one way for mentioning geometrical isomerism? None other molecules are having any restricted rotations? No. There are some molecules which are having restricted rotation. The most important one is rings. For example, if I am taking cyclopropane that is attached with the substituents A and B, how it will undergo rotation? How it will, this part, how that will undergo rotation? It's not possible, correct? So in that case, how it will form this kind of molecule B, A and A, B? This is not at all possible, which means that this is having restricted rotation. So this can also be possible in geometrical isomerism. Other than this, one ring system which is having a double bond, or which is having lone pairs of double bond, this system is also possible. Okay, mostly they will be asking questions from rings and double bond. Hope this is clear as far as now. Then we are moving to next part, that is RS notations. Naming R and S for molecules. We are naming it under the rules which is called can in whole prolonged rule, that is CIP rule. Okay, what this rule says? The first rule is that the group with the first atom having high atomic number is a senior. High atomic number, what we have saw in other examples also. High atomic number, that is priority 1. That is first rule. The second rule is higher mass isotope. Let's say I'm having isotopes for let's say hydrogen and deuterium, hydrogen and tritium, deuterium and tritium. So high masses, high mass isotope, that is senior, that gets more priority. Okay, the third rule is if I'm having a situation of the first atom of a molecule is same, CH3, CH2, the carbon which is same, the atomic number becomes same. In that case, I have to go to second atom. First atom same, then we have to move to second atom. Fourth rule, groups containing double and triple bonds are assigned seniority as both atoms are duplicated or triplicated of that. If I am having double bonds, which means that I am having two molecules of same. If I am having double bond CH2, then I should consider that as I am having two CH2 over there. If I am having triple bond over there, triple bond CH, then I should consider that as 3 molecules of CH is present over there. Depend on that, I have to give the seniority. And rule number 5 is bond pair is more senior to lone pair. Bond pair is senior or gets high priority than lone pair. Don't be scared of seeing these rules. It's just very simple. While solving the problem, while solving these examples, you will get to know. And there is a special rule I'll let you know while solving problem. Now, solve this problem to get to know these 5 rules and secret rule better. Before that, I would like to let you know R is for clockwise and S is for anti-clockwise. Okay, why I'm talking about the rotation now? Let's check it out. Here I'm having the first example. Hydrogen, COOH, CH3Br and Cl. So which will get more priority? Obviously, the first priority will go to Cl. Considering COOH and CH2Br, which will get more priority? Both are starts with carbon. So we have to look for second atom. That is rule 3 says, right? So second atom here, that is what? Here the second atom is bromine or hydrogen. Don't misunderstood, that is hydrogen. Don't do this blunder over there. That is Br. Because you can see this is attached like this. Carbon attached with Br. So you can take Br as a second atom attached over here. Okay. So what about here? COOH. Carbon is attached with double bond O and bond OH. Right? So the second priority goes to CH2Br. So the third priority is carboxyl group. And the fourth priority is hydrogen. Now, one rule you have to remember, that is, you are going to find the path, whether that is clockwise or anti-clockwise. In the journey, you have to remember one thing, you have to go via 4, not via 3. Okay? If 2 is not available. Here 2 is readily available nearby. So you can go by this way to reach 1. Whether that is clockwise or anti-clockwise. Is it clockwise or anti-clockwise? This is clockwise. So it becomes R. Right? So let's go to second example. Once again, the priority groups become same because I just took a same example in different position. But the groups are same, so the priority order will be same. Will that change the notation? Let's see. Cl, CH2Br. Okay. So I can go like this. Is it clockwise or anti-clockwise? It is clockwise. It should be R, but it is not. Why? There comes the sixth rule. Sixth rule says that if there is a fourth priority group on front of you or above the plane, you have to reverse the notation. So I can simply write the least priority group must be behind the plane or far from you. Ma'am, how to find above the plane or behind the plane over here in this kind of Fisher projection? In that case, you can take hydrogen must be in vertical position. Okay, hydrogen must be in vertical position. I mean, the least priority group must be in vertical position. Here that is in horizontal position. So I have to just reverse the notation. It becomes yes. And the third example over here, that is which is having 2 carbon system. If I am considering the first carbon, which is green color, you have to take this group as a single group, like we took for COOH. Okay, so in that case, which will get more priority? COOH or nitrogen group? Obviously nitrogen, because nitrogen atomic number is 7, carbon atomic number is 6. So first priority goes for nitrogen, second priority goes to COOH, third priority is for the group below, and the fourth priority is hydrogen. So least priority group must be in vertical position. Here that is not same, so I have to just do the opposite. Before that I have to find the clockwise or anti-clockwise, right? So this is clockwise or anti-clockwise. This is clockwise. Clockwise must be R, but I have to use the reverse rule, so this becomes yes. So let's take another one, the pink one. In this case, this whole group becomes a single group. Let me erase the above examples so that you can clearly see this. Right? The pink one, you have to consider that as a whole group, whole as a single group. So do the priority order of OH goes first priority, then here comes second priority, third priority group is again the whole above carbon, fourth priority group is hydrogen. So what is the rotation over here? Clockwise or anti-clockwise? This goes anti-clockwise, and the rotation must be yes, since hydrogen, which is in horizontal position, which is above the plane, so I have to take it as opposite side, that is R. So the first carbon yes, second carbon R. Similarly, you should do this example, fourth example, and let me know what is the notation for A carbon and what is the notation for B carbon. Okay, let me know in the comment section. The next topic we are going to see, that is optical isomerism. What are optical isomerism and what are optical isomers? Certain compounds can rotate the plane polarized light in a characteristic way, like clockwise or anti-clockwise, when it is passed through their solutions. These compounds are referred to as optically active compounds. But we can't see that by observing the molecule, right? But still we found some way to do that. First of all, what is plane polarized light? The ordinary light, the white light, which is an electromagnetic wave which has the oscillation of both the directions, like vertical and horizontal, right? But in case of plane polarized light, we made the white light as passing through the polarizer, which just made that as a like single plane, like one plane which is having the oscillation. Okay, that is plane polarized light. So here we are having two type of optical isomers, D and L, dextrorotatory and levorotatory. If the substance rotates the plane polarized light to a clockwise direction, then that is dextrorotatory. If that is rotating it anti-clockwise, then that is levorotatory. It is also mentioned as plus minus. Okay. So here one kind of question we can expect, that is asking for specific rotation. Specific rotation. What is that? It is a number of degrees of rotation observed when the compound is passing the plane polarized light. Okay, how much it is showing that rotation. Here we have the formula for that. Specific rotation alpha, which is equal to theta divided by L into C. Here L stands for path length. And C stands for concentration. Theta is observed angle of rotation. Okay. Sometimes they will give you the values of path length, concentration and the rotation angle. They'll ask you to find the specific rotation. So please be prepared for that. So this kind of question can be asked. And now let's move on to another important part, that is chirality. What is chirality? A compound which is non-superimposable to its mirror image. That is called chiral. Non-superimposable to mirror image, that is chiral. Okay, while a compound is superimposable to that mirror image, then that is called achiral. If that is superimposable, then becomes achiral. So how we can find that? We can find the chiral center. So what is chiral center is that? A compound in which carbon is attached with 4 different groups, which is lacking for symmetry, is called chiral carbon or asymmetric carbon. Lack of symmetry. We do have plane symmetry, plane of symmetry, axis of symmetry, and center of symmetry. Which lacks for symmetry, then that is asymmetric carbon, and if that is attached with 4 different groups, it is attached with four different groups. I'm talking about carbon, that's why I'm mentioning 4. 4 different groups, then that is chiral center or asymmetric center. Flakes of symmetry means asymmetric center, attached with 4 different groups means chiral center. We'll see the example. For example, if I'm taking a carbon that is having 4 different groups. This is chiral carbon, which can be denoted by the symbol star. Okay. Similarly, the asymmetric carbon can be denoted by the symbol star. Now we are moving on to the another important part, that is different type of writing a molecule. Different type of projections. Projection formula. What are the different types of writing a molecule? For example, we have wedge dash. We have Fisher projection. We have Newman projection. We have Soha's projection. These are different methods of writing a compound. First, what is wedge dash? Wedge dash is writing it with the three-dimensional system of, let me write it here, carbon, what are these? So here the simple dash refers for that substituent is on in the plane. It's on the surface, is in the plane. If that is denoted by like this, like wedge or dotted lines, then that is behind the plane or far from your way. Behind the plane. If that is mentioned as solid wedge, the former one is a dashed wedge, this is solid wedge, then that is above the plane, it's towards you. Okay, that is wedge dash. Talking about the next projection, that is Fisher. Fisher projection. Fisher projection of writing is writing as a cross. For example, we saw that in RS notation as well, like this. Okay, here how we can find it out whether that is above the plane or behind the plane. So which can be denoted as like this. The horizontal ones are above the plane and the vertical ones are below the plane, which is equal to this G, COOH and H. Okay, that is Fisher projection. Moving on to the next part, that is Saha's projection. Saha's projection is a molecule viewed slightly above, like top angle view. Like this. Or like this. Okay, this is kind of a top angle view of the carbon attached with the substrate. The final projection, that is Newman projection. Newman projection, which is like man standing over here, which represents the front carbon and the back carbon. It's like this. Here I'm having two carbons. What are they? The first one, let me take the dot, I mean the green one, which is represented by a dot, and I'm taking another one as in pink, which is here, that is round, right? So the dot one, the point, is represents the group attached with near to the eye. Okay, it's towards you. The dot is towards you. And the circle represents away from you. I mean behind plane, it's away from you. That is rear carbon. Okay, so that is Newman projection. How we can convert it? How we can do the conversions of one projection formula to another one? If you want, we'll do that in detail. Now I'm giving you just a simple example of this. For example, if I'm taking 2,3 dimethyl butane. Butane, so 4 carbons must be there. 2,3 dimethyl. So remaining hydrogens. For this structure, we are going to write all other projection formula. First, let's start with wedge and dash. Here I am having 2 carbons. Okay. So let's say I am having hydrogen on the behind the plane. One CH3. It's on solid wedge, which is towards you, and for another carbon, hydrogen is towards you, CH3, it's away from you, and one is on the plane. So I took wedge dash like this. Okay, depend on that how we can write it for other projection formulas. Okay, I'm considering these 2 carbons as a main carbon, front and rear carbons. So now let's go to the second projection, where I have the lines. So this and this carbon, one carbon is attached with two CH3s and one hydrogen. Okay. So here I am having CH3. So CH3 with CH3, right side I am having hydrogen, left side I am having another CH3. Note it down, these are opposite to each other. The wedges, solid wedges are opposite to each other. So how we have to write the opposite pair? That is one CH3 to another CH3 is just opposite. So CH3 opposite side, and then to that CH3 I am having hydrogen and another dashed with CH3. Now let's go to the third projection formula. Here I am considering CH3, this CH3 and another CH3 must be on the same side, or I can write it in the opposite side if I am writing like this. Both the CH3s are opposite, hydrogen are opposite. So because while doing the rotation, I can get it on the same side. That will equals to this texture. Right? Clear? So now let's see sawhorse projection also. So front and rear carbon. So front carbon, that is dot. So I'm taking CH3, this guy, and then CH3 on left side, hydrogen on right side. And if I'm considering the rear carbon, that is circle, so CH3 goes on the top and another CH3 on the right, hydrogen on the left. Okay, so this is as simple as that. I'll tell you, you can work on 2-bromo, 2-chloro-butane, and let me know if you are facing any problem while doing 4 other projections for this compound.